I'd like to talk about what happens when we anti-differentiate an expression that looks like this. First of all though, let's have a look at what happens when we differentiate something that looks like this. What we're going to do is draw a comparison and make sure we can work backwards. So if I took the derivative of an expression like this, let's say 3x plus 2 all to the power of 5. My answer will be 15 3x plus 2 all to the power of 4. So let's have a look at what happens and where these numbers come from. First of all, when I differentiate, you'll notice the power goes down by 1. Secondly, what happens is the original power and the coefficient of x multiplied together to get the 15. So ultimately, if I was going to summarize, the power goes down by 1 and the old power multiplied by the coefficient of x in the brackets, that multiplies the expression. And that's how I differentiate. So now let's look at these two processes and we'll consider them in the process of anti-differentiating a similar expression, because you can see your response here is a similar expression. And that means what we're going to need to do when we find the antiderivative of an ax plus b all to the power of r with respect to x, my power must go up by 1. And then, rather than multiply by the old power multiplied by the coefficient, I need to divide by the new power and divide by the coefficient. Let's have a look at this step here first. To divide by the new power is the same as multiplying by 1 over the new power. And to divide by the coefficient is the same as multiplying by 1 over the coefficient. Which means if I were to do this in a single step, my new power is increased by 1. So that's the same as multiplying by 1 over the new power, increasing by 1. And the coefficient is there. So this is what I'm going to multiply my expression by. Therefore, if I was going to take a formulaic approach, the antiderivative of this will be 1 over r plus 1 times a times ax plus b all to the power of r plus 1, and don't forget your constant. So here is the formula we will take when we find the antiderivative for such an expression. Now this is all well and good for all powers of r, unless r equals -1. Because if r equals -1 here, we end up with a term where we have 1 over 0, and we all know how much sadness and catastrophe that causes. So let's now have a look at the case where r equals -1. That means we're looking at this idea that I have the antiderivative of 1 over ax plus b. Because when r equals -1, this is in the denominator to the power of 1. What do we know from differentiation where we arrive at an answer of 1 over something? And what we know is that the derivative of a log will give us an expression like this. So the answer for when r equals -1 lies in our knowledge that taking the derivative of a log will give us such an expression. So now let's have a look the same way that we did over here in what happens when we take the derivative of a log. When I take the derivative of an expression, where I have log of ax plus b. Remember, my shortcut is going to be to put the derivative of this over this expression. So if you're not aware of that, if I take the derivative of log of f of x, my answer, that's log base c, my answer is f dashed of x over f of x. So therefore here, the derivative of this expression will be a over ax plus b. So therefore, if I want to go the other way and I want to consider this as a process, as a different sort of process, what I've done when I've taken the derivative, if I've multiplied by the coefficient and I have my expression ax plus b on the bottom. My log expression, whatever's in the brackets, will be in the denominator. So therefore, when I go the other way, what I'm going to need to do is I'm going to put my expression in the log, and then I'm going to need to divide by my a. Therefore, to integrate ax plus b when r is -1 with respect to x, or 1 over ax plus b dx, I need to first of all create my log expression with the denominator in the brackets, log base e of ax plus b, and then I need to divide by my a. Remember, going down this way I multiplied by the coefficient, coming back this way I'm dividing, so I end up with 1 over a log ax plus b plus c. Now that's almost complete, but there is something small that we need to think about, and it's got to do with these brackets. It seems like every time we do something here, we come up with a small exception, but believe me, this is the last one. When we look at the graph of a log, we'll remember that a log, it looks something like this, which means my domain matters for a log. Now here, it's possible that anything in this bracket could be positive or negative, but it must be positive because of the domain. So in this circumstance, we need ax plus b to be positive because of the domain of log. Now, when we have a situation like this, but we know we might get a negative number in here, one of the things we can do to consider is to place these two lines around it. These two lines are all about the modulus function. And what it means is whatever I have in this value between the two lines, I'm going to take the positive of that value. So the modulus of -3 equals 3. And the modulus of -17 equals 17. And therefore the modulus of ax plus b is greater than 0. And that means we can use it in our log expression all the time. So in summary, when we're anti-differentiating an expression like this, the value of r counts. When r doesn't equal -1, then the antiderivative of ax plus b to the power of r with respect to x will equal 1 over a r plus 1 times the original expression in brackets, all raised to an increased power, plus our constant. When r does equal -1, then this expression is actually a fraction that looks like ax plus b to the -1 dx, which equals 1 over ax plus b dx. And my answer is a log, and it's going to be 1 over a log base e of modulus ax plus b plus my constant. And these modulus lines are here to make sure we can deal with the fact that this ax plus b could be negative. And that's how we anti-differentiate that type of expression. If you found this or any of my other videos helpful, please subscribe to my channel or like the video. Thanks.